Okie dokie, artichoke. What's up, physics folky? This is Newton had a third law, and we're going to talk about this. Essentially, we need to review the first two laws first. So, Newton's first law, law of inertia. An object is going to stay in motion or stay at rest unless some outside force makes it change. Newton's second law. This is one we equate as force equals mass times acceleration. And it's very important to note, oops, that's a dot. Okay, there we go. What object is being pushed or pulled. And to be able to make our free body diagrams. So, if you are struggling with free body diagrams, please review our 5.4 as well as our initial 5.2 when we start talking about these and we start drawing all of our forces. Otherwise, I'm going to go ahead and assume that you are set with free body diagrams, or at least partially. So, Newton had a third law. Newton's third law goes something like this. For every action, there's an equal but opposite reaction. And essentially how that boils down is you cannot touch something without having that something touch you back. I know, weird, right? So if object A pushes another object, let's say object B, then object B will push object A with that same force, just in an opposite direction. Now here's the part that trips people up. So let's say we have our object A, and then we have object B. If object A and object B are applying equal but opposite forces, how come they don't just cancel out? Well, here's the thing. Force equals mass times acceleration. So the forces are equal, but if the masses are unequal, then you're going to have unequal accelerations, which means that the object will move. And that's how walking works, right? Yeah, that's awesome. The Earth, way bigger, way more masses than us. So although we apply a force to the Earth is so massive that the acceleration it feels is so minute that you're not even going to have to worry about it. You won't even be able to calculate it. It's so tiny. But because we are less massive, we are going to accelerate. And that's how we walk, run, jump, do somersaults and cartwheels and, dab and all kinds of fun stuff like that. All right. So let's do some practice. Let's look at Homer. Homer has a mass of 45 kilograms, and Bart has a mass of 25 kilograms. Now, what makes this different than other free body diagrams that we've done is that Homer and Bart are a system of interacting components, right? Bart is sitting on Homer's shoulders. So Bart is applying a force to Homer. Homer is applying a force to Bart. The ground is applying a force to Homer. So we have to deal with all of those forces. So the best way to do that is to separate them. So separate them into Homer and Bart. Afterwards, what we can go ahead and do is draw a free body diagram. That'll make it easier. And when you do this, you always want to start with the object that is not sandwiched in the middle of another object. So, for example, Homer is sandwiched between the ground and Bart. So I'm going to start with Bart because he is not sandwiched between anything. He's just sitting on Homer's shoulders. So, Bart, force of gravity going down, force of gravity, and that should be equal to Bart's mass, 25 kilograms, times the acceleration of gravity. So force of gravity should equal negative 250 newtons. Awesome sauce. Alright, now Bart doesn't fall, so that means that the same force is acting on it, just in an opposite direction this way, and that would be our normal force, or in this case, the force of Homer Simpson. Alright, and that should equal a positive 250 newtons. Excellente. Alright, let's look at Homer now. Alright, so Homer has his own gravity, right? And his gravity should be relatively larger than Bart's. And that gravity should equal Homer's mass, 45, times the acceleration of gravity, negative 10. And that should give us a negative 450 newtons. So that's Homer's force of gravity. But you'll notice that Bart is also supplying a force. And that one is negative 250 newtons, right? Because Bart is sitting on Homer. Jerk. So that means that in order to hold Homer and Bart, the ground needs to supply a normal force that is equal to positive 700 newtons, right? Negative 250 plus negative 450 gives you 700 down, and we need to have 700 going up in order to work. Now, after this, what we need to do is go ahead and circle our force pairs. Force pairs are pairs of forces that interact with the object. So whenever Homer and Bart are in contact with each other, they're exerting a force on one another, and that would be our force pair. So, force Homer, force Bart. They are equal, but in opposite directions. All right. You could also calculate the magnitude of that force pair. In order to do that, what we would need to do is look at how much Bart is putting on. In this case, it's 250. All right. Let's take a ninja and a hot dog. Hey, that's fun. Ninja and a hot dog. So what we have is a ninja and a hot dog. How many times can I say that and still not laugh? We have some forces that are acting on them, right? So in this case, it doesn't necessarily matter where you go. They're not really sandwiched between anything, but let's start with the ninja because that seems to be more fun. Force of gravity on the ninja. Yay, force of gravity. That's an F on the ninja, and that should equal the ninja's mass for 45 kilograms times the acceleration, negative 10, so negative 450 newtons. Then we have a force holding the ninja up. Now, because it's a rope or a string, we have what we call the force of tension. And that should equal a positive 450 newtons to make sure that this ninja doesn't fall. In this other direction, our hot dog, what we have is the force of gravity going down on the hot dog, and that one should be 5 kilograms times 10, negative 10, so that should be the force of gravity on the hot dog of negative 50 newtons, so much smaller than negative 450. In order to keep that from falling, this stand here or table needs to supply that same force. Positive 50 newtons going up, and that would be our normal force, equal there. Awesome. And because the rope is pulling on the hot dog, it should be pulling in this direction with the same force that this is pulling down. So for 50 newtons, and this is where it gets a little bit tricky. So this is our force pair. It's our force pair. But they have to be equal and opposite. Well, Mr. H, one's to the right, that's positive. One's going up, that's positive. What the deuce? How am I supposed to figure that out? Well, here's the trick whenever we have something on a rope like that. Here's our objects. Here's one. Here's our little pulley, and then here's our bigger ninja, right? If we were to take these forces in this rope and stretch it out so that it's linear. Let's see if this will let me do this. No. Let's just do one thing. If we were to stretch it out so that it's linear, it's that one. It's that one. They're equal but opposite, right? There's the force pair. Only thing is they're attached to the string. So whenever we have tension between two objects, we're going to have a force pair. All right. That concludes our awesome Newton's third law. If you have any questions, comments, thoughts, concerns, just want to talk about different things, let me know. Stop by my room, and I will see you later. Okay. Adios, amigos.